Compact objects are astrophysical bodies that have compressed into densities that are far larger than your average stellar density. So these are remnants of exploded stars or stars that have gone through like a red giant phase. Compact objects are interesting because if you're very near this event horizon where light's escaping, then you are in the realm of strong gravity. And so we can really probe the very strong regime of gravitational radiation or general relativity. One thing we can do with neutron stars and black holes as well is to constrain strong gravity. We do this right now. We do this with a number of different sources, ranging from relativistic binary systems with a neutron star and another neutron star, or a neutron star and a white dwarf, orbiting around each other in very close range. And the gravity is very strong in these systems. And we measure very, very good constraints on gravity. Of course, this has been a Nobel Prize awarded for this, and we've been able to show that Einstein's prediction of the gravitational wave equation is very precisely followed by these systems. Another thing we can do is try to measure or detect for the first time gravitational waves. Gravitational waves are slight disturbances in the space-time that pass through everything. And if it passes through the Earth, and we're measuring a pulsar very precisely, or in fact an array of pulsars very precisely, then the correlation between the timing of all those pulsars can give us a measure of the gravitational wave passing by the Earth. And we hope we can do that within the next 10 years. One big field of research is on knowing or understanding what is happening at the interiors of the neutron stars. So neutron stars are so collapsed. They're in a very dense state of matter that we don't see anywhere else in the universe. So this dense matter is in a state where you have neutrons leaving the nuclei. And the neutrons are floating around just free. The pressure of the neutrons themselves is actually holding up the star against gravity. And so in this state, we don't really know what else there is. There might be more exotic species than just the standard neutrons and protons. We might have quark matter. We might have kaons. We might have something we haven't thought of yet. But we can get at the nature of the interior of the neutron star by looking at the characteristics of the neutron star itself.
There was a lot of talk about magnetars in this particular session. What do we know so far about them, and what can we hope to learn from them in the future?
Well, we know magnetars are neutron stars with extremely strong magnetic fields. So they have the strongest magnetic fields in the universe, as far as we know. Those magnetic fields on normal neutron stars are something like 1 million times higher than you can measure on Earth. They're 10 to the 12 Gauss in those units, but for magnetars, we're talking about 100 to 1,000 times higher than that. So these magnetic fields are, they produce very extreme processes that we don't see in even other normal neutron stars like pulsars. So we see very exotic processes going on near the surface. And we hope we can measure these at some point with the right detectors. The thought that you have something that's the mass of the sun rotating at hundreds of times a second, where the speed of the surface is actually 2/10 the speed of light, to me is just mind-blowing. But that's the surface of a millisecond pulsar. So you can imagine. And plus, the high magnetic fields as well. I mean, the things you can do with very high magnetic fields is very interesting physics as well. So I've just been fascinated by very strong magnetic field physics my whole career. So to find magnetars, something where you actually can, you can't avoid strong magnetic field physics is fascinating. So, well, there are a number of upcoming X-ray detectors, particularly, and one of these is called the Neutron Star Interior and Composition Explorer, NICER is the nickname. And that's going to launch in 2016. And it will, well, it's hopefully going to measure the radius of a neutron star to within an accuracy of 5%. And so if you're looking to constrain the equation of state of the neutron star, then this will actually be, a very big leap